So, last time we looked at positive definite binary quadratic forms and equivalence classes of them under the action of SL2Z. We defined what a reduced binary quadratic form is, and we proved that any equivalence class of a positive definite binary quadratic forms contains exactly one reduced binary quadratic form. So, today we are going to look at many examples of how to compute all reduced binary quadratic forms of a given discriminant, and we will look at, if you are given a binary quadratic form, how do you find an equivalent reduced binary quadratic form. So, let us do the second one first, but before that recall what a reduced binary quadratic form is. A positive definite binary quadratic form is called reduced if, so let me denote that by A comma B comma C, if two conditions are satisfied. So, first, so we will always assume that A and C are both positive. Mod of B is less than or equal to A is less than or equal to C, and the second condition is that if mod of B is equal to A or A is equal to C, then B is greater than or equal to 0. Okay, so, that is what reduced binary quadratic form means. So, let us take a binary quadratic form of a so let us take something complicated like okay, maybe before that. So, if we are given a positive definite binary quadratic form ABC, we can repeatedly use the following steps to find a binary quadratic form, a reduced binary quadratic form equivalent to ABC. And what is the first step? Well, the first step is if C is less than A, then replace by C minus B and A, right. Secondly, if mod of B is bigger than A, then replace by A B plus 2 K A and some C prime. Okay. And what is K? K is simply floor of A minus B by 2 A. Okay. So, let us do this in an example. So, let us look at an example. So, the example that I have is 458 x square plus 214 xy plus 25 y squared. So, this binary quadratic form is 458, 214 and 25. Okay. So, if you really want to compute its discriminant, then you can. This is 214 squared minus 4 into 458 into 25, right. So, if you do this, you will get something like 45800 here, and then 214 square. So, this is 200 plus 14 squared, which is 40,000 plus 196 plus 28 into 200, so 5600. So this is 4, 5, 7, 9, 6. Yeah, so 4, 5, 7, 9, 6. This is minus 4. Okay, so that's kind of very nice that you have all these big numbers, but the discriminant is simply minus 4, and this is chosen for a particular reason. There is exactly one reduced binary quadratic form of discriminant minus 4. So, just by knowing that it is minus 4, I know which one we are going to get, but let us do this calculation anyway. Okay, so here we want so A is bigger than C, right. So, we replace this, right. So, 458, 214, 25, this is equivalent by using 0 minus 1 minus 1 0 to 25 minus 400 and 214 458, right. But now what you have is B mod B, which is 214, is bigger than 25, right. So, you take K to be floor of A minus B. So, 25 minus 214 by 50. So, floor of this, which is 225. So, 4, right. Okay, so we replace that by this. So, 25 minus 214, 458. This turns out to be equivalent to 25 minus 14 and 2. Yeah, so I think I made an error last time in something that I claimed. I will put that in the erratum, not do it now. Okay, so this is using 0, 9, sorry, not 0, that makes no sense. 1, 9, 0, 1, right. Okay. So, again I can apply this. So, 25, 14, 2, this is equivalent using 0 minus 1, 1, 0 to 2 minus 14, 25, right. So, again B is mod B is bigger than 2. So, you take K to be 2 plus 14 by 4 floor of this, which is exactly 4. In fact, you do not have to, it is an integer, but anyway. So, 2 minus 14, 25, this is equivalent using 1401 to 2 to 1. Then again that thing 2 to 1 is equivalent using 0 minus 1, 1, 0 to 1 minus 2, 1, right. Okay. And so, again we are in the same issue that mod B is bigger than 1. So, you let K be 1 plus 2 by 2 floor of this. So, this is 1. So, you replace 1 minus 2, 1 by, I think I did something wrong, 2, 2, 1. Yeah, I think this should still be what? 2, 2, 1. Oh, I did not need to do that, sorry. What am I doing? Yeah, I did not need to do that, right. Okay, my notes say something different, but I want to do here, yeah, I want to do something. Okay, so my notes say something different, but let me let me do this. So, but this should not be 1, this should be 2. I had made a mistake there anyway. All right, so so that thing, and then if I replace this should be 2. So, if I replace this by this, I get 1 here, and then minus 2 plus 2a. So, that will be 2. So, this is 0, and then this turns out to be 1. So, this is 1 0 1. Okay. So, 458 x squared plus 214 x y plus 25 y squared is equivalent to x square plus y square. Okay, so that is kind of amazing that after doing all this, this is the reduced form we get. So, that is the algorithm to find reduced forms equivalent to some given form. All right. Okay, but how do you find? So, the next question that we are going to try to do is, how do we find all reduced binary quadratic form positive definite of a given discriminant? But let me do a proposition before this if it is not obvious. There are only finitely many positive definite reduced binary quadratic form of a given discriminant. Okay, so there are only finitely many ABCs. Okay, so proof. So D is fixed. Okay. Then there are only finitely many ABC such that B square minus 4AC is equal to D, and mod B is less than or equal to A is less than or equal to C, and the other thing is not even needed, but if this or C is equal to A, then B is greater than or equal to 0. Okay, so there are only finitely many things like this, and why is that? Well, you first okay, so so you know that D is B square minus 4AC, and we know that so this is negative by the way, and we know that A is bigger than mod B, bigger than or equal to, and C is bigger than or equal to mod B as well. So, AC is bigger than or equal to mod B square, which is same as B square, right. So, instead of subtracting AC, if you subtract a smaller quantity, you get minus 3B square. So, 3B square is less sorry, what did I do? Yeah, sorry, if instead of subtracting AC you subtract a smaller quantity which is B square, then you will get something which is bigger, right. So, 3B square is less than minus D, which is bigger than 0, right. So, B square is less than minus D by 3, and so there are only finitely many possibilities for B, b, right. And now you have again d square equal to b square minus 4ac, which means that 4ac is equal to d square minus b, and this is a positive integer, right. This is a positive integer. So, this has only finitely many factors, right. So, this has only finitely many solutions, right. So, that is how you get that there are only finitely many reduced binary quadratic forms of a given discriminant, right. And so, now we are going to try to find them all, and the way to find them all is you basically just try all possible values of b. Okay. So, yeah, so the proof also tells you how to go about finding all possible values of b, right. So, example, let us find all reduced binary quadratic form of discriminant. So, you see discriminant is always congruent to 0 or 1 mod 4, right. So, minus 1 is not 0 or 1 mod 4, minus 2 is not 0 or 1 mod 4, minus 3 is not 0, minus 3 is 1 mod 4, right. So, the smallest thing we can take is of minus 3, right. So, let us say discriminant minus 3, okay. Then we can take minus 4 or minus 7 and so on, right. So, anyway, let us take minus 3, d equal to minus 3. So, b is less than or equal to square root of minus d by 3, which is equal to square root of 1, right, which is we are just taking positive things. So, mod b is always between 1 and minus 1. So, we can just try out those things. So, we know that 4 AC is equal to b square minus d, right. So, we just try out various values. So, of b. So, b is equal b square equal to 0 gives you 4 AC is equal to 3. This has no solutions, right. Or you can have 4 AC is, so now you can take b square equal to 1. So, you get 1 plus 3. So, AC is equal to 1, and so you get A equal to C equal to 1, and so you have B is also equal to 1, because you have to take B to be positive, right. So, there is precisely one reduced binary quadratic form of discriminant minus 3, namely x squared plus xy plus y squared. Okay, so that is it, and you see that the discriminant is minus 3 indeed. Okay, let us look at d equal to minus 4, right. So, again mod b is less than or equal to square root of 4 by 3, which is less than 2. So, again b square equal to 0 or 1. So, 4 AC is equal to, but now there is a difference. So, when b is 0, you get 4 here, and so A is equal to C, A times C is 1. So, A is equal to C is equal to 1, and so there is x squared plus y squared. But when b is equal to 1, 4 AC is equal to 5, and this has no solutions. So, again there is precisely one binary quadratic form of discriminant reduced binary quadratic form of discriminant minus 4. Okay. Let us look at one more example. I take d to be minus 20, then mod b is less than or equal to 20 by 3, which is roughly square root of 7, and so this is less than 3. So, b square is equal to 0, 1 or 4, right. Those are the possible values of b square, because the possible values of b are 0, plus minus 1 and plus minus 2. So, let us say b square is 0. What do we get? 4ac is equal to 20, and so ac is equal to 5, and we want a to be less than c, and both are positive. So, a is equal to 1, c is equal to 5, and so we have 1, 0, 5 as one possible binary quadratic form. Now, let us take b square equal to 1, then 4ac is equal to 21, and this has no solutions. B square equal to 4, then 4ac is equal to 24, and so ac is equal to 6, and so a is equal to 2, c is equal to 3, right. So, there are yeah. So, again the possible values of b is plus minus 1, but b is equal to minus 2 is not allowed, as mod b is equal to a, right. So, the only other possibility is 2, 2 and 3. So, there are two equivalence classes of reduced binary quadratic forms of discriminant minus 20. So, there are two reduced binary quadratic form of discriminant minus 20, right. So, that is again amazing. Okay, yeah, maybe yeah. So our next task, so maybe that is all for the examples. Our next task would be, so what we are going to do is we are going to do the following. We will relate the ideal class group of q square root of d to the equivalence classes of binary quadratic forms of discriminant d. Okay, so d is a discriminant, d is not any arbitrary integer, d is a discriminant of a binary quadratic form. And so, what we are going to do is we are going to relate the ideal class group of this to these equivalence classes. And how do we do that? Let us get started today, and I will finish next time perhaps. Yes, so we can do the following, right. So, let okay. So, let d be an integer d less than 0 and d is congruent to 0 or 1 mod 4, right. So, that is how we know that it is going to be a discriminant, and let k be q square root of d, d is square free. Okay, maybe I do not care about square free actually. D is this, because it could be 4 times some square free number, right. So, the only yeah, it could be 0 mod 4. So, yeah, so let's this be as it is. Now, let A be an integral ideal in OK, and let us say that A is generated over Z by alpha 1 and alpha 2. Now, what I do is I take any alpha in A, I can write alpha as x1 alpha 1 plus x2 alpha 2. I can take norm of alpha, norm from k to q of course. So, let us say Galois group of k over q is, it will have order 2, right. So, there will be one trivial element and one non-trivial element. So, this will be alpha times sigma alpha, right. So, I just write this in terms of x 1 and alpha 1, x 2 alpha 2, and x 1 and x 2, x 1 x 2, these are integers, right. So, sigma does not do anything to them. So, this is x 1 sigma alpha 1 plus x 2 sigma alpha 2. So, if I expand that out, what do I get? Norm of alpha is equal to x 1 squared alpha 1 sigma alpha 1 plus x 1 x 2 alpha 1 sigma alpha 2 plus alpha 2 sigma alpha 1 plus x 2 squared alpha 2 sigma alpha 2. Now, it is clear that alpha 1 and sigma alpha 1 and alpha 2 sigma alpha 2, these are integers, because alpha 1 and alpha 2 are algebraic integers. These are just norms of alpha 1 and alpha 2. But it should also be clear that alpha 1 sigma alpha 2 plus alpha 2 sigma alpha 1, this is also an integer. Why is this? Because this is symmetric. Sigma of alpha 1 sigma alpha 2 plus alpha 2 sigma alpha 1, what happens when you apply, you get sigma alpha 1 and sigma squared alpha 2 plus sigma alpha 2 and sigma squared alpha 1, but sigma square is identity, right. As sigma square is equal to 1, you get sigma alpha 1 alpha 2 plus sigma alpha 2 alpha 1, right. So, sigma fixes this element, which means it has to be in the field of rational numbers, but it is also an algebraic integer. So, it has to be an integer, right. Okay, so, norm of alpha from k to q is some a x 1 squared plus b x 1 x 2 plus c x 2 squared. So, this looks like a binary quadratic form, is not it, right. So, this looks like a binary quadratic form, but you can, this is not quite the one that we want, right, because so if you look at determinant of this matrix alpha 1 alpha 2 sigma alpha 1 sigma alpha 2, right. So, if you look at this, this will be norm of A into discriminant of K. Why is that? Well, this is kind of obvious, because this will be equal to whatever the index of A in OK is times the discriminant, and this index is norm of A times discriminant of K. Okay. All right. So, but you see this quantity we have already seen at the top of this page. This is alpha 1 sigma alpha 2, well, not quite with the plus sign, but with the minus sign. In any case, yeah, let me write it down. So, alpha 2 sigma alpha 1, yeah, okay. So, how is norm of A defined? Norm of A, this is the ideal generated by norm of each element in the right. So, this is, we proved earlier that this thing is equal to A times sigma of A, right. So, in particular norm of A divides alpha 1 sigma alpha 1, alpha 2 sigma alpha 2 and alpha 1 sigma alpha 2 plus alpha 2 sigma alpha 1, right. So, what you do is you replace your, so you divide out, so you take norm from k to q of alpha divided by norm from k to q of norm A. Another way to see that there is divisibility is by saying that this is an algebraic integer, right. So, this will be alpha 1 sigma alpha 1 by norm of A. I will forget about the subscript alpha 1 sigma alpha 2 plus alpha 2 sigma alpha 1 by norm of A x 1 x 2 plus alpha 2 sigma alpha 2 by norm of A x 2 squared. Okay. So, I will denote this by A, B and C. So, A, B and C. So, you get A x 1 squared plus B x 1 x 2 plus C x 2 squared. Okay. And you can show that this thing is independent of the choice of basis up to equivalence. So, we have associated a binary quadratic form to, so this is the binary quadratic form associated with A. So, next time I will show that this association is indeed well defined, so which means that if I choose a different basis I get an equivalent binary quadratic form, and so what you get is a so what you get is a map from non-zero integral ideals into the equivalence classes of binary quadratic forms of a given discriminant, and then we will actually show that if you take two equivalent ideals they give you the same equivalence classes of binary quadratic forms, and so you will get a bijection from the set of ideal class group into binary quadratic forms. Thank you.